In this video tutorial, we're going to be talking about attosecond photoionization time delays. My name is David Busto and I'm an assistant professor at Lund University. But first, let's start with the basics. Here is a schematic representation of an atom that is composed of a series of bound states that converge to the ionization threshold. Beyond lies the ionization continuum, which is composed of infinitely many states. Unlike the states below the ionization threshold, the states in the continuums are free states, so that if we promote an electron from a bound state to the continuum, this electron will escape and the atom will be ionized. The kinetic energy of the escaping electron is then simply given by this equation, where Ek is the kinetic energy, hν the photon energy, and Ip the ionization potential. This equation is at the basis of all photoelectron spectroscopy. If instead of ionizing the atom with monochromatic light, such as synchrotron radiation, we now use a short pulse that contains many frequencies, we will now populate a broad range of continuum states. In this case, if the coherence properties of the electron are transferred, of the light are transferred to the electron, then we can describe the electron with a photoelectron as a photoelectron wave packet characterized with a spectral amplitude A of E and a spectral phase delta of E. Before we continue to explain how this relates to photoionization time delays, let's go back to optical pulses. Here we have two pulses, one propagating through a medium with refractive index n and thickness L, and one propagating in vacuum. The pulse that propagates through the material will acquire a phase phi that depends on the frequency of the light, and after propagation through the material, it will acquire a phase shift delta compared to the pulse that propagated in vacuum. This phase shift corresponds to a delay in time, which is simply given by the spectral derivative of the phase shift. If we now move on to matter waves, such as photoelectron wave packets, a similar phenomenon can happen. We can have an electron wave packet that propagates in a potential V that we can compare to an electron wave packet that would be propagating in vacuum. Again, the electron wave packet propagating through the potential will experience a phase shift and give rise to a delay known as the Wigner delay or Eisenbud-Wigner-Smith delay given by this equation. In the case of photoionization, this is known as a half scattering event because the photoelectron wave packet only experiences half of the potential. For this reason, we can still define a time delay, but it is now given by half of the original delay described in the 60s. At this point, it is important to mention that this Wigner delay is not the delay corresponding to the transition from the bound state to the continuum. There is no time associated to this transition. It is also not the time that the electron takes to escape the atom, because the Coulomb potential has infinite range and this is ill-defined. This delay really corresponds to the asymptotic delay between an electron that propagates in vacuum compared to an electron that propagates in the potential. So how can we measure these delays? The first technique is the streaking technique. We can use an isolated attosecond pulse to ionize an atom, for example neon in this case, and if the photons have sufficient energy, they can ionize the atom from two different shells, such as the 2p shell and the 2s shell. Because the 2s shell is deeper, the electrons coming out from there will have a lower kinetic energy, giving rise to these two photoelectron peaks. In order to obtain time information, we then superimpose a short, intense infrared pulse. In this case, depending on the electric field at the time where the electron is created in the continuum by absorption of the attosecond pulse, the electron will experience a kick either to higher kinetic energy or lower kinetic energy. As a result, by changing the delay between the XUV and the infrared pulse, we can obtain a spectrogram like this, both for the 2s shell and for the 2p shell. Using then a retrieval algorithm, it is possible to extract the relative delay delta tau A between the 2s electron and the 2p electron. An alternative method is the rabbit technique, which stands for reconstruction of attosecond beating by interference of two photon transitions. In this case, we use a train of attosecond pulses, which in the frequency domain corresponds to a comb of odd harmonics. Here, we only represent two harmonics, which in both cases will give rise to two photoelectron peaks, both for the 2p shell and for the 2s shell. Here, in order to obtain temporal information, we superimpose a relatively long and weak infrared pulse that now can induce continuum-continuum transitions. For example, for the 2p shell, an electron can absorb the lower harmonic and absorb an infrared photon, or absorb the upper harmonic and then emit an infrared photon. These two quantum paths interfere and give rise to the formation of sidebands. Depending on the relative delay between the XUV and the infrared pulse, the photoelectron yield in the sideband will oscillate, so that when we change the delay, we will obtain these two spectrograms for the 2p electron and for the 2s electron. In this case, the temporal information can be directly obtained by comparing the relative phase between the sidebands from the 2p electron and the 2s electron. At this point, it is important to mention that neither the rabbit nor the streaking techniques give direct access to the Wigner delay. The delay that is measured using this technique is known as the atomic delay, which in atoms can be decomposed as the Wigner delay, which is target specific and heavily depends on the exact shape of the potential in which the electron propagates, and a continuum-continuum delay, which is universal and is the same for all the atoms. This continuum-continuum delay can then be subtracted from the total delay, giving access to the Wigner delay. It is important to mention that this is only valid in atoms. In molecules and in solids, this decomposition does not work. The photoionization time delays have been measured in a large variety of systems, in atoms, molecules, and condensed phase. They provide detailed information on electron correlation, electron-nuclear coupling, and propagation effects in materials. For more information, you can look at these different references, which are reviews dating from 2012 to the most recent one that only targets atoms.